Hi guys, hi once again, and welcome back. So for today, I think I picked another medium question. Just been working through the mediums, not knowing if I should do easy or hard, but mediums are mostly my favorite. And today I think I picked like probably a pretty probably should be famous because has a high number of likes and for sure I think the number of submissions to are pretty high. Sorry for my face being in the corner, but I think today, as once again, never solved it, and I've probably heard about it so many times that I've never solved it. So today, it was like on my lead code problems. All I think it was like for one to solve today. So once again, I just decided to take a look at it. So they said you're a professional robber planning to rob houses along the street. Each house has a certain amount of money stashed, and the only constraint stopping you from robbing each of them is that adjacent houses have security systems connected to it. So basically, you can't, if house A and house B are adjacent, if you rob house A, you can't rob house B. If you rob house B, you cannot rob house A, sort of. You have to go rob maybe house C, the next house after robbing house A. House A. So basically, that's it. So given an integer array names represented amount of money in each house, return the maximum amount of money you can rob tonight without alerting the police, which means that you can only do it in one night. So so like for instance in this one like this 1 2 3 1, you if you decide to rob house one, you have to rob house three, and that's it, which means it's four. It makes sense because if you decide to start with house two, you you can only go rob house one later on, which will be three unless. So from the question also, one thing we should keep in mind is that basically they're also telling us that they. So from the question, if you rob house one, it doesn't mean necessarily you have to go rob house three. If you rob house one, you can go rob house four, depending on how whatever works out. So that's what I get from this question. So and then in this case, also as an example, you rob house two, you can't rob seven, you go rob nine, you can't rob three, you have to rob one. So nine plus two is 11, plus one is 12, which is why it's 12. Makes sense. You can't rob house, you can rob house seven, but you have to go rob house three or house one. If you rob house two, you have to go rob house nine, three, or one. If you decide to go for nine, you'd have to either go rob only one. If you go from two, if you decide to go to three, that's it. From two, if you decide to go to one, that's it. So we have to keep that in mind. So basically, for a question like this, I'll give you guys a couple of seconds to probably think through. You can pause the video and just think through, like maybe if you guys have any solution in mind. As I always say, I always think through the problem with you guys. As I'm talking, I'm literally thinking through the problem as well. So normally, whenever there's something like this with an array, you can guess there's always going to be a brute force solution. And at least in an interview, it's said that if you can't even think about an optimized way, at least think about a brute force way. So probably the brute force is definitely to try out all the combinations, and we can tell this is just gonna have like a very bad runtime because you'd have to try this with this and then that, or this with that, and then like let's say you try one with three, or you try one with one till the end, like that same sequence, or now you go try two with one, or now you try three. So in this case like this, you have to try two with nine, two with nine, two with nine, two with nine, and one, two with three, two with one, before you go to seven, seven with three, seven with one, or go to nine, nine and one, or go to three and go to one. So basically, you can tell how in raised to the power something, it's probably going to be n raised to the power something. So something very polynomial, if not even exponential, but it's bad runtime. So I'm assuming in something like this, they probably want you to do it in a better runtime. So I'll give you guys some time to think about this. But for me, there are a couple of things that are coming in my mind. So some people would say dynamic programming, some people would say however it is, but normally a fun fact about me is the time I started, before even taking a dynamic programming course, I had already started thinking about problems in dynamic programming. I didn't even know what's called dynamic programming yet. So don't, if dynamic programming is a scary thing to you, trust me, most of the time you're probably thinking about a problem and you don't even know it's called dynamic programming, but it's dynamic programming. So dynamic programming is just, for me, how just, if you see sub problems or something, how to solve it faster. But that's for another day. So for me, what I see with a problem like this is, for example, let's say looking at this first problem, 1 2 3 1. I know that, I think, okay, how can I do it in a very fast way or a very good way? Which means that to do it in a very fast way, I was thinking, okay, so one, if I'm at one, normally I know that before I know the value here, okay, let's even start here. Before I know the value here, imagine if I was here at house one, and imagine the thief standing at house one and saying, oh, I'm at house one. Right after house one, which of these houses should I rob next that would optimize or make me have the most amount of money? Do you get it? So it's like, at house one, what house should I rob next? Because obviously he can't rob house two, but out of house three and house this out of this house, oh sorry, out of this house and this house, like out of house with money three and house with money one, which house should he go to? Like, it's like as if you're giving the thief some predictive ability. Which house should he go to that he knows that, like, he's gonna get the most money? Obviously, imagine he didn't know house this house has $3 and this house has $1. But we want to give the thief a predictive ability in the sense that now you can choose between house three and house one, like house with $3 and house with $1. But which of them should you go to make the most money? Do you get it? So the only way we can know that is if somehow he has information on that, or he gets like a tip from someone. But the only way he can get a tip is if someone knows these houses. So which means, and that knowledge has to be passed to him. So what does that mean? So that means that before he even gets to house one, he needs to have some information about either house three or house four to know which one to go to. So how do we give that information to him so that he has that predictive ability to just go to those houses fast? Because in that way, then we will get it in a fast time. And in programming, we know that we can only, or one of the ways to do that is to store the information sort of in a hash map or a dictionary. So that's the first way I think about it. And this is a kind of problem that I think you have to solve it, or a good way to solve it is to work backwards. So, see, I have not mentioned dynamic programming, I have not mentioned any of those scary concepts, but see, just think simple concepts. But at the end of it, those that know dynamic programming will know that I'm probably talking about dynamic programming. But you see, I didn't even have to mention dynamic programming here. So how about, because the thing too is they didn't specify we have to start from the start here, which means that it could even be that there could be scenarios, or like we could have an example where, let's say it's 0 1 0 3 4. Sorry. So it could even be a scenario where starting at the start does not necessarily guarantee you the most amount of money. Do you get, I don't know if what I'm saying makes sense. So in this case like this, we know that what is the maximum amount of money? The maximum amount of money he can generate is 5, because he starts at this house here, and then he goes to house 4, because he just can't go to here after 1. He can either go to 3 or 4. But if he goes to 3, he can't go to 4. So he'll just get 4 instead of 5. Do you get it? So we want it in such a way that when the thief is at house 1, he has the predictive ability that I should rather go to house 4 rather than house 3 to make the most money. Do you get it? So that's what we're trying to do here. So basically, the best way to do this is we need to start from the back. And why do we start from the back again? Because if we decide to start from the front, we're assuming that he's always going to start at 1. But it could even be the case that starting at here is the most optimal way, which is true, because if you start here, you will have the most optimal route starting from here rather than starting from here. So that's another trick in this question. So as I say, I'll keep this example here, but let's go back to our previous example. So So this is how I was thinking about our problem. So not to talk anymore again, let me go through a solution so you guys understand what I'm talking about. So basically, what we're doing here is we're starting from this part here, 1. So we start from 1. So from 1, we know that with 1, the next jump. So as he said, you can, all you have to do is you can only do a jump, like, how do you call it? So imagine we were here. We know we can't jump here. So the next index we can jump to is either here or any other combination of that. So we can either do an even jump or an odd jump of a certain amount. So let's say for index I, we know we can do a jump of I plus 2 or I plus 3 or any other thereof. So if what I'm saying makes sense. So that's the first thing we should keep in mind. So imagine that here we say, okay, at 1, what can we jump to? So we can't jump to anything. So at this point, the maximum, if we decide to start here, is at this jump 1. But now we go to 3 and we're saying, okay, at 3, where can we jump to? We can jump to 1. No, we can't jump to 1. We can jump to I plus 2. So at this index, this is 0, 1 to index 2. Index 2 plus 2 is what? Index 4. So we can jump to 4, index 5, or any of thereof. But we know that those don't exist in LS yet. So, but then what we do is we check that we still keep this index. So how do I put it? So we have like a hash map or a dictionary. Where in our dictionary, let's say we had index. So we started from here, which is index 3. So we have index 3, and we know that the max at index 3, when we are at index 3, the maximum we can get is 1. Money 1. So now we go to index 2, and then at index 2, we know that the maximum here we can get is 3. Because at index 2, we can't go to 1. But now, imagine we're here. If we're at index 2, if we're at index 1, which has money of 2, we know that once we start at index 1, so keeping this index, we know that we can jump to 1. Thus, we can jump from index 1 to index 3, 4, or more. So we check. So what we do is we have like the jump. So let's say we say jump to something like that. So jump to, we know will be that index I plus 2, or we have another jump to. Let's say odd jump to, which is I plus 3 thereof. So we know that when we jump to 2, if 2 is in the list, like if we jump to the next one, we know we already don't have to calculate this guy already, because at this guy here, we already have the best possible value. So if we jump here, we know at index 1, we know at index 3, sorry, I confused the indexes. We know at this house, we know the value that's there because we just checked the index of it and we know it's index 3. So at index 3, we already know the maximum amount of money we can get. Do you get it? So at this place, we know when we jump here, we just return whatever results we get from here. So and then in that case, because at index 2, we know we can jump there at index 2, we will keep in our dictionary at index 1, sorry. So in index 1, we know it will be the value of index 1, which is 2, plus whatever value we get from wherever we can jump to. So we know we can jump to here, which is index 3. So plus dictionary of like 3, because we know that's the max, because this value, it will tell us what we can, the maximum we can get. So I don't know if what I'm saying makes sense. So index 1, this is what we get. So it will give us a value. So let's say at index 1 like this, we'll get 2 plus whatever is at index 3, which is 1. So we have 3 here. So we also check if we can do an odd jump, but we know an odd jump that's an I, that's 1 plus 3 will take us out of range, so it's not possible. So now we go to 0. So now we know our highest is 0. Our highest is 3, because these are the amounts. But yes. So now we go to 0. So now at index 0, now we see at index 0, if we do an even jump, so index 0 plus 2 will take us to index 2. So 0, 1, 2 to take us to 3. So we know it's either going to be 1 plus 3. So we see it's 1 plus 3, or or this index 1 again plus the maximum of when we jump to index I plus 3, which is 0 0 plus 3, which is index 3. This is index 3. So, or when we do a 1 plus 1 jump, so we know we get one of them to be 4, we get one of them to be 2. So we pick the highest one, so we know it's going to be 4. So in the end, we can see that we will have the maximum here. We can try it on this one as well, 27931. 27931, and then we can try it on this, and then we can try it on another one. Let's say 2112. So let's try it on 27931 and let's see what goes on. I'm sorry this take long, but like just to make sure you guys understand it. So we start again. This is 0 1 2 3 4. We start at index 4. We know at index 4 the maximum we can have value is 1. We go to index 3. We know index 3 the maximum we can get also is what, 3, because that's the maximum we can do. So now we check at index 2. Index 2 would be 9 plus index, whatever index we can jump to. We know we can do an even jump, so let's just call it even jump 2. So we know we can do an even jump, like sort of to 1. So we can jump to this index, so it will be either 9 plus 1, 9 plus 1, which is 10. So we have 10. And then now at index 1, we know that at index 1 we can either jump to 3 or we can jump to 1 or thereof. So now at index 1, we know if we jump to 3, it's going to be 7 plus the index at 3, which is 3, or 7 plus when we decide to jump here, so it's going to be 1, which is 8. So we get 10 or 8. We choose the maximum. So what do we get? We know we have an 8. Do you get it? So we know in the best case scenario, we choose the best case scenario. The reason why we choose the best case scenario, 7 plus 3 rather, so it's 10. The reason why we choose the best case scenario is so that when the thief is at behind, he knows the best house to get to. We're giving him that predictive power so that he knows automatically that, if I'm at this place, I should probably go to this house then. Do you get it? Because this house has the next highest value from all the back. And the reason why this is the 10 is because from this point, this has the best value. So now at 0, we at index 0, we know it's going to be 2 plus either he jumps to index 1. And at index 1, we know it's 10. Do you get it? So see, you see what's going on here? Now he knows he has either he goes to here, which will give him the 10, and it will be the 12, or he can jump to 3, which will be 2 plus 3, which would be just 2 plus index 4, sorry. 2 plus index 3. Index 3 here in the dictionary is 3. So 2 plus 3, or he can even jump here. But the reason why it's just better for him to jump here, we don't even need to go here, because if not, we'll just do it will be like a whole linear thing again. We're just looping through everything again. But the reason why we don't need it is because at this point here has captured the best scenario out of everything here. Do you get it? Because if he jumps here to here, we know he can jump here again. Do you get it? This guy here, whatever index we have here at index 4, this index 4 has captured the best possible value it can have. This index 3 has captured the best possible value. That's why we just do 1 even and 1 odd, because at this even jump, it's captured the best possible value it can get. So, or we can do the 0, 2 plus 10, or 2 plus 2. So, he can decide to jump to 1, but the reason why it's not necessary to jump to 1 is because this 9 here has already captured the best scenario. Because 9, you remember at 9 here we did 9 plus 1, which was 10. So this guy here has already captured the best scenario, this guy here. So that's why we just either do 2 plus 10, 2 plus the index at 2, or so index at 2 is 10, or we just do 2 plus index at 3, which is index at 3 is 3, so 2 plus 3. So So you get either 12 or 5, and we know 12 is the best answer, so we choose 12. So now what we just have to do is we just have to look through the dictionary values and then choose the highest one. So, or if we don't want to do that and we want to do it along, so we just save a little bit of time, we can also do that as well. So basically you have the idea of what to do. Now we can try one last example before we start coding it up, just to make sure everybody understands. So this one, 2 1 1 2. Let me just take this one out. You know what, let me just take this one out. Let's do 2 1 1 2. So in this case, if you decide to start from the start, the reason why it's not always beneficial here, if you decide to start from the start, 2 1 1, because if I take 2, I have to go to 1 here, and if I take this one here, I can't go again. That means my maximum is 3. But so in this case, my maximum is 3. So but see, if I take 2, I can start here at 2. Actually, if I take 2, I don't have to go to this 1. I can go to this 2 straight away. So I can get what? I can get a 4. Which is why we don't just do a jump to just jump over it one time. We can jump over it twice or as many times as we want. See, but we will see the reason why this predictive power is important. So that as soon as it finishes robbing from this house, it knows that don't go to this house rather. Even though we know we can't go to this house, but don't go to this house. Because if you go to this house, you won't be able to go, but rather go to this house. See, we need to give that T that predictive power. And how does that happen? Let's start with the dictionary again. So if we start with the dictionary, at this index 3, that's the last here. We know the maximum we can get is 2. Now, if we go to 1, no, that's index 2, which is this one. We know the maximum we can get is a 1 if we start from there. Now, if we go to index 1, we know the maximum we can get is this value 1 here, the value at this index 1 plus the value after it does the jump, which is 1 plus 2 3. So at dictionary 3 or at index 3, and at index 3 in dictionary 3 we know the highest value is 2, so it's either 1 plus 2, which is 3. So we know it to be 3. Did you get it? So now at index 0, that's where the magic happens. Now at index 0, we know it's going to be 2 plus whatever. Now the first case is either 2 plus it jumps to here. So now in here is at index 0 1 2, it's at index 2. At index 2 we see it to be 1. So 2 plus 1, or 2, which is itself, plus the index of when it jumps to the next one, like I plus 3. So 0 plus 3 is 3. So we take it to index 3, and index 3 is what? Index 3 has a value of 2. So this plus 2. And so it's either 3 or 4. Did you get it? So in that case, we choose the maximum. You get it? And so it's 4. So in this case, you see, it gives it the predictive power that jump to the 4th house. That's index 3 rather. So do you guys get what I'm doing here? So this is how we're going to write the program. So at least if you have this idea now, maybe as I code it down, maybe you guys will understand so far what I'm trying to do. But I hope you guys have a gist of what I'm trying to do. So basically we will definitely have our dictionary. That's our predictive power thing that helps the thief see it, or the tip, because in what we have is always that. And then we can just, as I said, either in the end we just check through the dictionary values and then choose the maximum, or we can just be selecting the maximum along the way. But I think it's just better to select the maximum along the way, so that as soon as we're done traversing through everything, we're just done. Because if not, we'll have to go through the dictionary values again, and that probably will take like an ON time again. So it's still better than polynomial, but it just makes it more faster. But I mean, it doesn't matter. The most important part is just this. So I'll just go ahead and just do this. So we can just set our maximum currently, or highest money, or we can just say total rob. We can set total rob maximum to be like, let's say, the last value of the list, because I said we'll start from the back so that it can give that predictive power model. So we start from the back, and in that way we know it's gonna just be nums -1 just for the last item. So as I said, we're gonna start from the back, so we know it's gonna be for I in range in Python, we just go len of nums -1 to -1 -1 in the reverse order. So we know we're gonna start in this reverse order way. So what we just have to do is, now we have it this way. So all we can do is we can have even check, or even jump, or we can just have any of them, but we can just have an even jump to even jump 2, or yeah, even jump or even check this house. Let's just call it check. Not really a thief jumping around, but sure. Even check, which is equal to that I plus 2, as we said. So plus 2, and we can have an odd check, which is equal to I plus 3. So now we know we have these two. So we can then say, now we can first check. So what we can do now is just say if even check in dictionary. Let's just pass them for now. Do something. If even check not in dictionary, do something, which we'll go back to later. Now we check if odd check in dictionary, do something. If odd check not in dictionary, do something. So now we just know that. Now we know that if they're all in the dictionary, because we have to make sure, like for instance, we start here and we just do an even check. We don't want to have an error from Python saying index out of range. We just need to make sure first that it's in the range. Do you get it? So we first have to check if it's in the range or it's not in the range before we can do whatever we have to do. So and we can't just insert into the dictionary. So we can just say if even check in dictionary. So let's first assume, like starting from the back here, we know it's not going to be in the dictionary. So let's say it jumps I plus 1. If it's not in the dictionary, we know that even insert something to insert into the dictionary. So even inserts, we know that we have to put in the dictionary. As we said, if this one is not, that would be the highest we can put into the dictionary. So we know that in the dictionary, even to insert is going to just be, it's going to just be I, which is just going to be that. If odd check is not in dictionary, we also know that odd in sets is just going to be equal to that same I, or that value it is going to be. So sorry guys. So I think so far, just take a break and let me know if you guys get what has been gone so far, but not to waste any of your time again. So we know that, oh sorry guys, so we know that's what we're gonna do. So what do we do next? So but if our even check, that's the jump we're gonna go to if we already found it in dictionary, because before we get here, if there's any jump that is appropriate, we're gonna have these values already in dictionary, or these indexes already in dictionary. So that's one thing we have to just know already. We know that they're gonna already be in the dictionary. So if even check or odd check is in dictionary, then we know that even check should be equal to whatever value that is there at that index that we're currently at. As we said, if we're here and we want to check whether we have to jump to 3 or 1, it's going to be either 7 plus 3 or 7 plus 1, or 7 plus whatever is at index 3 that has been stored in the dictionary, or 7 plus whatever is in index 4 that has been stored in the dictionary. So it's going to be this word plus dictionary of that index. So if that index is already in dictionary, so even check. So if it's not odd check, then we have odd check equals num I plus dictionary odd check. So now we don't just insert into the dictionary yet. See, we have to compare and see within the even check and odd check which one is bigger. So we now insert into the dictionary whichever one we think is bigger. So we know dictionary I, let me just space it out a bit. So dictionary I should be equal to the max of even check and odd check. Now, after we do this, we know that we can just wait to finish the whole program before we check the values, but also we can just find the total robbed already. As we said, total robbed will also just be max of either a total robbed already or the dictionary I, because at this point it's just keeping the max. So we just compare it to the max like this. So in the end, all we just have to do is just return total robbed. So this should work, but maybe there might be a few errors or so, but this should basically work for most of the scenarios. So let's just see. Oh yeah, there's a space here, so that's true. So that should be it, and I'm hoping it works. Oh, snooms. Sorry guys, snooms. Probably just a few of them now. Snooms. And then yeah. Should be working for now. Let's see what goes on. Oh, so it's given an error saying 1231 is returning. Oh, I see. So, mm, okay. Total raw. This. We have our even check. We have our odd check. What is going on? So, okay. This made sense. So I don't even know why this is not working. Unless I am. Unless I am messing around. Let's go through this together, guys. Let me just make sure. So 1, 2, 3, 1. We insert. Yes, we always insert if it's that way. We go, we go, we go. Ordinate set equals that. So actually, that is very surprising. Why it's not working? Because it should be working. It really should be working. So -1, -1. It goes 2, 3. Check. Or check. Oh. Oh, I see why it's going that way. It's supposed to be even insert and then odd inserts. Makes sense. That's why it's not working. It's supposed to insert, not the check. It's the insert, what we are to insert. But hold on. Even check, odd, odd inserts, even inserts, even inserts. So, check, even check, odd check, odd insert. Oh, I see why. It's supposed to be inserts here. Makes sense. Alright, sorry guys for being so long. This has been a very long video. It didn't have to be, but yeah, I guess. So we're gonna run it against our example test cases just to see. Oh, come on, guys. Okay. In the meanwhile, let's just put it against what we did some time ago. And then I remember one of them we had like 0 at the start, and I think 3, 4, 1, 0. You can try so many things, but let's just try a couple of them and see what happens. Yeah, all 4 test cases passed, so I'm guessing that's supposed to be it. And then you can run it just again for good luck. Alert, please, and let's submit to see what goes on. See, so perfect. So wow, great. Thank you guys. This was pretty fast, as I said, very fast. It's uses less memory actually, because now it's just. Also, the reason why it's probably a little bit more faster also is because it's getting the. We're already checking the max already on the start. And this was just my genuine idea. I've not looked at it anywhere. This is my first time ever solving it. Believe me or not, but once again, let me know what kind of questions you guys want me to solve, and I will always solve them. And thank you guys very much for being part, and any concept that you want me to explain. I know I'm bad at explaining. I also actually like whiteboard explaining, so if you guys want me to do it whiteboard and stuff, let me know. And see you next time. Thank you. Bye.